Well, students, today we are going to start a new topic that is called dual nature of matter, or de Broglie's. It is also pronounced as de Broglie, actual pronunciation de Broglie, dual hypothesis. It was found by Louis de Broglie. And then next point which we will be studying is de Broglie wavelength of an electron. What is the value we will be reducing, and we will also experimentally demonstrate the wave nature of an electron. Okay, now when de Broglie suggested the material particles of motions should display wave properties, the wave properties, then what did he do? He gave some assumptions. Now, what are those assumptions? First, he said that number one assumption that is the Einstein's mass energy relationship, that is the relation between energy E equal to mc square. This is called Einstein's mass energy relation. There is a complete equivalence between matter and radiation. So that is what is called matter means there is a relation between, or you can say equivalence between. You can say there is an equivalence between this first instance mass energy says that complete equivalence between matter, that means mass, and the next thing is radiation. So radiation, and that means what is that radiation? Radiation means energy. So this is the first assumption upon which the dual nature is based upon. The second assumption is that nature loves symmetry. Nature loves symmetry. What is the meaning of that? Nature loves symmetry. That is, since the radiation has got dual nature, so matter also should possess what is called, since they are having equivalence. So if nature loves symmetry, then what will happen? Radiation has got dual nature, so matter also should possess dual nature. So in that way, electrons, protons, neutrons should not only behave like mass points, but they should also exhibit wave nature. So the wave associated with these particles were called de Broglie waves. They were named as de Broglie wave. Okay, this is the second assumption. The third assumptions he gave was, we can rather say that since the wave associated with it gave nature loves symmetry, and from this we can say that there is a dual nature shown by radiation as well as matter. So since there is wave nature, so we came out with a term called wavelength. Okay, this is called de Broglie's wavelength. It is actually deduced from this one, de Broglie's wavelength. Now, what is the de Broglie wavelength? Now, the length of de Broglie's wave, that is, it is the length of this de Broglie's wave, that is de Broglie's wave. The length of the de Broglie's wave was called the de Broglie's wavelength. So these are the assumptions. Now, in order to deduce the de Broglie's equation, or you can say rather wave equation, Planck said that what did he say? That quantum theory of radiation, that is, energy is exhibited in not continuous but discrete in the form of packets, and it was given by E equal to h nu, where h is called the Planck's constant and nu is the frequency of radiation, E is the energy. Okay, this is h is the Planck's constant, named after the scientist Max Planck. So if from Planck's quantum theory and from Einstein's mass energy relation we are having E equal to mc square also, that means h nu, that is h, from these two what must we get? H nu must be equal to mc square. That means now next it should be h nu is frequency nu is equal to velocity of light. What is it? C. Velocity of light is c by wavelength lambda. So nu is equal to c by lambda. So we can write nu is equal to c by lambda equal to mc square. So this c and one c goes. So what remains is h by lambda equal to mc. Now it is actually mass into velocity. So this mass into velocity, is momentum. So we call it P. That is, it is equal to momentum of photon. Photon is what? The particle of light. Because product of mass and velocity we know will give momentum. And this momentum is the momentum of the particle photon. So we get lambda equal to h by lambda equal to p, or lambda equal to h by p. So this is an expression for wavelength and it is called de Broglie's wave equation. It is called de Broglie's, or you can say de Broglie's wave equation. Okay, so this is a general formula and can be applied to photon. This is a general formula and it can be applied to photon as well as any other moving particles. So we can write, if you can write it for any particles, that means lambda equal to h by p can be written as h by m into v also. In place of c, we can write it v, where v is the velocity of any moving particle. So this expression lambda equal to h by mv, okay, lambda equal to h by mv is considered to be the momentum, and it is characteristic of particle with wavelength, which is the characteristic of a wave. So these are the what is called expression of the de Broglie's wave equation. Now we come to some conclusion from this wave equation. So we have seen assumptions. Now let us see what are the conclusions of this assumption. So as a result of this conclusion and as a result of the equation, we come to an expression lambda equal to h by p equal to h by mv. So now we must have a conclusion about this expression which we have got. First is that from this expression it is clearly visible that lambda is proportional to 1 by v. Why? H is constant, mass is also constant. So lambda is proportional to 1 by v. And it also means that faster the material particle, smaller is the Broglie's wavelength. And the second equation the second conclusion is that number 2, lambda is inversely proportional to 1 by m also. That means lighter the moving particle, is higher will be the de Broglie's wavelength. Right? From it is inversely proportional, so it is possible. And then we have the third conclusion. What is it? That the de Broglie's wavelength of the moving particle is independent of the charge and nature of the particle. It does not depend on the charge or the nature of the particle. Now, fourth conclusion is that number 3 is does not depend on what? Does not depend on charge and nature. charge and nature of whom? Of particle. These are the three conclusions, and then let us come to the fourth conclusion. Now what is that fourth conclusion? That is, after getting the three conclusions, lambda inversely proportional to 1 by b, lambda inversely proportional to 1 by m, lambda does not depend upon charge and nature of the particle. Next comes if, fourth one, if v equal to 0, that is if the moving particle is at rest, lambda equal to h by mv. Now division by 0 is not possible. V becomes 0, what will happen? Lambda will become equal to infinity. That means you cannot visualize such waves, okay, if they are in motion, because the wavelength will be very high wavelength, infinite, okay. So these are the, and also there are some other what is called conclusion, that is some other conclusion, like what will be the conclusion? Some other conclusions are there, like it is concluded that de Broglie's wave, matter wave, that are not electromagnetic waves, but because waves are produced by accelerated charged particles, whereas de Broglie's waves are produced by charged as well as uncharged particles. That is, de Broglie's wave or matter wave are not electromagnetic waves, because you know that from definition of electromagnetic waves, they are produced by accelerated charged particles, but these are all these waves are produced by charged also as well as uncharged particles. And then we have, if the material particle is moving with a speed which can be compared to the speed of light, then it is seen that the mass of the particle will be m, that is relativistic mass, m naught by root over, this you will get in higher studies, 1 by v square by c square. Then de Broglie's wavelength is lambda is equal to h by mv. So this m can be substituted by the relativistic mass. Next is number 7th conclusion is that macroscopic objects like ball, stone, vehicle, etc. do not show wave-like properties. Because why? Because mass of the body is large. Mass is large compared to speed for macroscopic bodies. Macroscopic bodies. Okay, so because of that, they do not show wave-like properties. They do not show wave-like properties, wave properties. And finally, we know that Heisenberg's uncertainty principle we have studied in chemistry. Here it is impossible to measure both position and momentum of moving particle same time accurately. Position as well as momentum cannot be determined accurately at the same time. So at the same time, all you cannot know. This is by Heisenberg's principle. By Heisenberg's principle. So this is all about the conclusion from the experiment. That's all for now. In our next video, I'll be giving you the de Broglie's wavelength of an electron. Thank you.